All right. Good morning, good afternoon, good evening, ladies and gentlemen, and a happy new year. This is the first video in 2024, and just thought I could talk about homotopy, which is a topic in uh, topology. And basically, I'm just going to give you um, insight into the topic and maybe run through a few examples. So we're going to talk about homotopic and homotopic equivalent spaces. Equivalent spaces. All right. So I'll start with homotopic spaces. And let me give you the general idea. So suppose you have the letter H. Okay, so this is the letter H. And basically what you want to do is you want to transform this letter H to this type of letter H. And the key idea here is that you can reduce these points. So these points can collapse into themselves, okay? And when these points collapse to themselves, they can become simply this letter H. Now, what we are looking at spaces, we're trying to observe what is happening to the letter H at different times. So we'll give the full time that it takes to go from here to here as time 0, or let me say included 0 to time 1. So let's say this is the time it takes for this H to turn into this H. And basically, if we are able to continuously collapse the points into itself, towards itself, and we are able to come up with a new space, then we say these two spaces are homotopic, and that's basically the idea. So let me define it formally, then we can look at an example, and we see how we can go from there. So two topological spaces, Basically, this is how we can formally define homotopy and homotopic. Okay, so two spaces x comma tau of y and y comma tau of x, such that the mapping of f and g from x to y is continuous. F and g are homotopic if there exists some function that is governing this transformation, such that the function at time 0 just brings out the function f, and at time g, at time 1, we get the function g, and throughout this process from time equals to 0 to time equals to 1, the transformation is continuous. I'll give the same example of the h. Suppose we have the h that we had, and this would likely be the f, and we want to see if it is homotopic to this h here. Now this would be g, and now this h has a small hole there. All right, so now remember, the idea is to collapse the points into itself so that you have a complete H. Okay, so now at time 0, quite all right, we're going to have f. That is what is happening here. At time 0, we're going to have f. Now let's look at time equals to, let's say before we even get to 1, at time equals to half, say. At time equals to half, we're going to have something like this. So let me say it will reduce a bit. This is at time equals to half. We'll reduce a bit. like that. Okay, to reduce a bit. But here there will still be a hole because there is a hole here. And basically, this hole will cause a discontinuity because as this is going down on itself, as it is collapsing, there are 2 points that are going away from each other. And if you remember the limit definition or the simple definition of limit, then you know that this is a discontinuity. All right, so this would conclude that since there is there is a discontinuity at this point, then we can say that these two spaces are not homotopic. All right. All right. So that makes us conclude that the two spaces are not homotopic because of failing to meet this requirement. So basically for homotopic spaces, to determine if two spaces are homotopic, we just have to test these three conditions and we are good to go. So let's look at an example. So let me just paste an example here. All right. Okay. Let X, so this is like the space where F belongs and Y is the space where G belongs, be two subspaces. All right. Or let me say this, there is a mapping from X to Y. Okay. And F and G is such that we can map the points from X to Y. So this is one direction. They are defined by this. So basically F of theta is equals to cos of theta, comma sine of theta, and G of theta is equal to cos of theta plus 1, comma sine of theta plus 1. So these two spaces are homotopic, but we have to show it. Okay, so how do we show that the two spaces are homotopic? We need to find a function f. Okay, we need to find a function f that has x and t such that when you take the function at time equals to 0, you get your f, and you take your function at time equals to 1, you get your g, and you need to show that f such that you're moving from 0 to 1 in time, this is continuous. So this is what we have to do. So now how do you find this function? So that's where the issue is. Well, you can parameterize f and g. So the simple parameterization is you take 1 minus t, then f of theta plus t g of theta. So this parameterization will most likely work in like 90% of the cases. So you use that parameterization to find your f. So in this case, f of theta times this. So we're just going to have theta times everything here. So that is just, let me put it like this. It will be 1 minus t cos theta and comma 1 minus t sine theta plus t, then the g, which has cos theta plus 1 sine theta plus 1 here. Okay, let me bring it. And sine, comma sine theta plus 1. And let's see if we'll get f at time equals to 0. So x comma 0. So where there is 0, where there is t, we put 0. So if we put 0 here, we remain with 1. We put 0 here, we remain with 1. And this 0 will cancel this out. So what will just remain with is, here we remain with 1 times cos theta, which is just cos theta. Then comma here again will just be sine theta. And we clearly see that this is equal to f of theta. Okay, so condition 1 has been verified. Okay, I'm going to erase this due to space. So let's try condition 2. At time equals to 1, when I put 1 here, it will be 1 minus 1, 0, 1 minus 1, 0. So I'll just remain with this part. So just have cos theta plus 1, comma sine theta plus 1. Okay, and we can clearly see that this is g. Okay, this is g of theta. Okay, so we have shown this part. Then now the part that we have to show is the continuity of the function f. Okay, so basically f is such that you have x comma t. You can use the epsilon delta definition to do continuity, but I'm just going to give a brief on this. Let me say a brief talk about the continuity. We know that sine is linear, sine theta is linear throughout the plane. Cos is also linear, and t is linear, so we can conclude that the entire function will be continuous throughout the plane. Okay, so that is, but you can show the continuity using epsilon delta or the topological definition of continuity. Okay, so that's just about it. So for homotopy, you just need to satisfy the 3 conditions between the 2 spaces. The conditions have been satisfied. We say the 2 functions are homotopic. Now we come to homotopic equivalence. Okay, homotopic equivalence. Okay, so two spaces. I will say 2 spaces. Let's say x comma tau of x and y comma tau of y are homotopic equivalent. Okay, if the mapping between f and g from x to y, or let me say if the mapping from x to y and g from y to x, so you can tell that g is the inverse of f, is continuous. And if these two are inverses, what we expect is that when you take f of g, let's say of x, what you're expected to get is x. And when you take f of, g of f of x, what you're expected to get is y. And basically what we can say here is we just say the identity of x, and here we can say the identity of y because it will depend on the function. Okay, so basically this is homotopic equivalence. Now to explain it simply, we are looking at spaces that let me say, if they can be reduced to the same space, or they can be reduced to a point, then we can say the two spaces are homotopic equivalent. I'll give an example of an H, okay? H and this point here, okay? So here, are we able to reduce this point to H and vice versa? So that's the difference between homotopic equivalence and homotopy. Okay, so we're able to move from here to there and from there to there. So that's the general idea. Okay, so let me give two spaces that are homotopic equivalent. Say the letter A, okay, as we were given in class, the letter A and the letter D. Okay, so if you check the letter A and the letter D, this part can be deformed so that it forms this part of the D, and this part can be deformed so that it forms this part of the D, and these 2 points can be contracted to form the ends of the D. Okay, so you have basically moved from this point to this point, and you can also move from this point to this point by simply, these points can be stretched and you would have an A. Okay, so that is the key idea in homotopic equivalence. You can move from this point to this point and the other way around. So that is why you need to show that when you take f of g of x, you get the identity of x or the identity of f, and when you take g of f of x, you get the identity of g. So basically, that's it. All right, so I didn't want to make a long video, so for tonight, that is all. Have a great evening.